Hello, guys. So we just covered the syllabus, and hopefully, if you have questions, you're gonna come up with those questions during the office hours or I call it the lecture discussion. And since it's asynchronous, so I'm just gonna continue and cover the next topic, which is the first topic in this class. It's gonna be the big picture. So this is not part of the book. This is something that I usually start with to at least introduce my computer science students to what is computer and what is organization and what's programming. Okay, so as I said in the syllabus, the outcome of this class or the main idea is that you understand the organization of the computer. So organization, sometimes they call it architecture. Okay, so they mean, they both mean the same thing. So organization, for some scientists or for some scholars, organizations and architectures are not the same, but majority, they believe it's the same. So we will understand how a computer is organized. And once we know how the computer is organized, we will learn how to program it. So as I said, hopefully at the end of the semester, you will understand what is the computer, what is the architecture, and what is programming. So let's get started. Okay, so hopefully in this today's slides, you can understand the differences between microprocessor and microcontroller, and what are they and the differences between them. And I hope that you also going to understand the difference between or the differences between the main two computer architectures and the main differences and identify the core differences in an architecture. And hopefully you would understand what is instruction set architecture. Okay, and you're going to see like how those main two architectures, the one that you learned right here, how they're going to be implemented. Okay, so we're going to focus on one of them, and then we're going to see how the industry actually implement those architectures. Okay, and we're going to look into the hierarchy of a programming paradigm. All right, so let's get started. Okay, so we're gonna first talk about what's a computer today. All right, so let's look at what's a computer, and then we're gonna focus on computer organization or architecture, and then we're gonna talk about programming. All right, so if I ask you what's a computer, right? If you look at those devices, they are computers, right? That's the desktop, the laptop, okay, and so on and so forth, okay? The smartphones that we all use on a daily basis, these are all computers. Okay, so what are the differences? So the only thing that you can see right now is the shape, right? So we don't care much about the shape. That's maybe because of mobility, right? So this is a desktop is really hard to move. And this is a laptop, it's movable, right? So the smaller the CPU, or I mean the computer, the easier you get to move it around. But we're focusing mainly on organization. Are there differences in terms of how these computers are organized? So that's the whole idea. So if you look at what the computer is a mechanism, right? That is the whole idea. So the main idea of the computer is you have an input, right? And you have a central processing unit, and you have an output. So you have the I and you have the O. So all of these, I believe, they direct the processing of data that comes from the input to the CPU, right? And they perform the actual processing of the data inside the CPU, and they're gonna actually produce the output, the result, out to the output unit. So you have input unit, CPU unit, and the output units. All right, so these things actually happens based on a program. Okay, so you need to have a program that takes the input to the CPU and then process it and get it out. One program that is very well known, we don't write this program, is the operating system. All of these computers, they need the operating system. Why? Because when you press on the keyboard, you need a program that takes that signal to the CPU, process it, and once it's ready, the CPU will tell the OS, and the OS is gonna print it out. So the OS is the program. Okay, so that is very important. So we need to understand what's a computer. So the computer is a mechanism that takes an input, processes it, and produces an output. It doesn't matter. And that happens all with the help of what? with the help of a program. So I will show you this. So let's first look at this point. So this is a C code or a C program. This is a data type, which is an integer. We're going to cover it in this course as well. And that is the scanf. So the scanf is the input. So that's the I. Okay, so this program right here, the scanf is a program. It's not a command or it's not a function. It's actually a whole program that's going to read data from the user and is going to store them in A and B. So A and B is something inside the CPU. So A and B is part of the CPU. So the keyboard, the scanf is going to read from the keyboard, which is the I unit, store them inside the CPU. Part of the CPU is memory. Okay, so it's going to store it in the memory A and B. Okay, and then once we do this, then we need to process. So that is the plus, that is the processing, because A and B are just memory, things inside the memory. So where is plus? That means addition. We would understand this in this class very well. So inside the CPU, there is something we call arithmetic logic unit. So that's when we have the add instruction in there. So that's the processing inside the CPU. Okay, and that is the program actually. Without this program, this is not going to happen at all, right? So the whole idea, input unit, output unit, CPU, it happens with the help of a program. Okay, and if that is the case, then now we need to see the output because the result is already in the memory, is already stored in the sum. So we're just going to get the sum and we're going to print it out. So print it out is what is the output, is the thing that's going to present the output. And usually this is going to be what? This is going to be the screen, right? This is going to be the monitor. All right. So this is mainly what it is. All right. So that's what a computer is. So this is the desktop computer. These are like the input unit. It could be the mouse, could be the keyboard. The output, it could be the monitor. It could be the speaker. Okay. And this is what we call the CPU. It has the microprocessor, the memory, the hard disk, and so on and so forth. Okay, and this is also a computer, right? This is a smartphone, and this is a laptop. These are, again, computers, and this is the input unit. This is the output unit, right? And the CPU is inside there. This is also, the input is the monitor, the output is the monitor, and the CPU is inside. And this is what we're going to look at just in a minute. Okay, so these are the input devices and the output devices and the screen devices, right? So let me go back a little bit. Maybe I went ahead of myself. Okay, so if you look at this desktop, that is the desktop right here. This is the motherboard. This is the CPU, inside the CPU, inside the box. So when we say the CPU, we mean actually the microprocessor, but usually that's not the case. When we say CPU, we mean the microprocessor, we mean the memory, we mean right here the monitor. These are all slots inside this board. That's why we call it mother, that holds all these components. Okay, so this is the main memory. This is the CPU. If you look at this CPU, we have the picture right here. This is something that's going to cool it down because a lot of heat comes out of this CPU. So you have the fan and you have some material on top of it to cool it down. Okay, so these are the slots for the out. This is actually the keyboard. Can you figure out where the keyboard is? This is usually the USB keyboard, right? So this is going to be the input unit. This is the output. This is the memory. This is the processor. Okay, so these are the main components of a motherboard, of a desktop. This is for a laptop, so it's the same. We're going to go back to the same idea. It's input, CPU, and output, right, guys? So it doesn't matter whether it's a laptop or whether it is a desktop. It doesn't really matter. You have a motherboard that holds those I/O devices, the input and the output devices, and the CPU. When we say the CPU, we mean the microprocessor and the memory. Okay, so this applies right here, and this is also true for a smartphone. It's the same. You have the same motherboard, but the size is really tiny, right? But it holds the same components. All right, so again, it's input, CPU, and an output. It doesn't matter. So just a computer is a mechanism that takes an input, process it, and produce an output with the help of a program. Whether that program is an operating system, is a code that you write, or whatever that program is, okay? So if you look at these components right here, are those computers? Is a car a computer? Is the smartwatch a computer? is the micro, uh, the remote control is a computer? Is the microwave a computer? Is the washing machine a computer? Are those computers? Okay, let's think about it. Do they take input? Yes. Let's look at the microwave. It takes the input. The input is going to be, are you going to cook something or are you going to heat something up? Just going to provide the time. That's the input. And then you choose the program. Okay, and we have something inside we call the CPU. And then the output is going to be after you hear the beep, right? So after the beep, you're going to say beep, beep. That's going to say it's ready. That's the output. Okay, how about the remote control? Some of the remote controls, they take an input as a sound, right? You speak. So it's a speech. You speak, you say it's CNN or Fox News, and it's going to send the signal to the receiver, and the receiver is going to process the signal, and then is going to connect it with the TV, and this is going to show you the channel. So it takes an input, process the input, it knows it's a CNN, and it sends the output. So it's a computer. Okay, so the question remains is, I mean, the question that I'm trying to raise, or I'm trying to make you think about, it is not the shape that makes a computer, it's something else. And let's look at what that thing is. So if you look at those devices that we looked at right now, these are like traditional computer. This is what we call, these systems are not computers, but they have a computer as part of it. Okay, so this is a car system, a transportation system. This is a washing machine system. This is a cooking system, right? It is not actually a computer. I mean, by it, the whole system is a computer. No, it is not. The whole system is not a computer. The whole system is something else, but computer is a component of it. That's what we call embedded system. So the computer is embedded within the system, whether it's a car system, whether it's a remote control system, whether it's a gaming system, whether it's a watch. This is a watching system, right? Whether it's a washing machine system, the computer is there to control some functionality. Okay? So at this, but it doesn't matter. Both of these systems, they take input, they have CPU, and then they produce an output. It doesn't really matter, right? So we want to know the capabilities. So if you use the normal, like desktop or laptop or smartphone, they use microprocessor. If you want to embed the computer system within another system, this is what we call microcontroller. Okay, so the microprocessor is powerful. Okay, microprocessor right here, if you look at it, the CPU and the I/O functions are packed as what? Separate. You can look at it in here. That's the CPU, that is the memory, that is the monitor. You see, that is the keyboard, that's the printer. You see what I'm talking about? So these parts are out of the microprocessor. Whereas in the microcontroller, we don't have a motherboard because it's not a computer system. We just need a chip that is going to be on top of a mechanical or electronic or electrical parts and control its functionality, part of its functionality. So that's the microcontroller. So the microcontroller, it has everything on one chip. So this chip has the motherboard, has the CPU, has the I/O, has everything in one chip. Okay, so that's the difference. So most I/O functions are integrated into the same package, okay, with the CPU. So that is, the CPU has everything in here. It has the microprocessor, it has the I/O and everything. The CPU right here is different. This is part of the CPU, which is microprocessor, and this is the motherboard, and these are the I/O devices. Okay? So there are different type of microprocessor. In this class, we're going to mainly focus on microprocessor, not microcontrollers. If you actually are going to do computer embedded systems, you're going to learn more about microcontrollers. Okay? If you Arduino, if you have ever used Arduino, which is the similar to the Raspberry Pis, okay? So Arduino, they use microcontrollers. They don't use microprocessors. Okay, so in this class, we're going to focus mainly on x86. Okay, during the last at least 2 years, I also, during fall and spring semester, my students use Raspberry Pi and they learn about ARM as well. but this is not something that we're going to do in this class. Okay, I mean, during summer, we're just going to focus on x86. This is Spark, is a Sun Microsystems. Sun Microsystems is the company that created Java. So they use a microprocessor they call Spark. Z80 is made by IBM, okay? And AMD is also another microprocessor made by Intel, but we're going to focus mainly on x86. All right, guys. So these are the type of microprocessor. This is an educational microprocessor. They call MIPS. Many universities or many courses that they cover computer organization, they teach it using MIPS. But in this class, I decided to go with x86. It used to be Spark before I come and teach this class at GSU. I just changed from Spark to x86 because of usability. They have a lot of material, a lot of support, a lot of tool that deals with the x86. And I believe the future is going to be for the ARM. So that's why I integrated ARM as part of this course, but I do that only during the regular semesters. Okay, so this is the x86 family. And looking at the x86 family, we have multiple families in here. We're just going to focus on x86. You have x286, x386, x486, and so on and so forth. We're just going to focus on this family, 86 family. Okay, so there are multiple microprocessors in there. All right, so this is ARM. This is a microprocessor that is completely different from x86, which is Intel. So different in terms of what? Again, in terms of organization, if you want to call it that way, or in terms of architecture. It depends on how you look at it, okay? All right, so now hopefully you understand what's a microprocessor, what's a microcontroller, and what's a computer, and what is the differences between them. So we're going to look at architecture, computer architecture. What's computer architecture? So if you look at the computer architecture, every computer, as I said, it's going to have an I/O, input-output, okay? It is going to have a memory, and it's going to have a central processing unit, right? That is the microprocessor. And you can see the bus that links all of them right here. This is what you call the system bus. And we have different type of buses. We're going to talk about them later. But this is a very high view of what a computer is. If someone asks you what a computer is, that's what the computer architecture is. CPU, memory, I/O, and buses. That's it. So those buses, they're going to take the signals from the input to the CPU. And inside the CPU, we're going to have the microprocessor, right? So you might say, hey, but you already said that the memory is part of the CPU. Again, it depends on how you define the CPU, okay? So the reason we say the main memory, it is because of the schools that we have, or the schools that actually separate the main memory for one reason, and that is something that I'm going to explain in the upcoming slide. But you need to understand that the computer organization or the computer architecture, that means these four main parts. So keep that in mind, please. Okay, so we have two main type of architecture. Van Neumann, this is the commonly adopted in industry, and this is what x86 is using. And we have Harvard architecture, and Harvard architecture is nowadays coming back to life, and it's heavily used in the cloud. Some of the cloud computing, they use Harvard architecture. So if you look at the picture right here, if I ask you what is the difference between those, let's look at it. So CPU, CPU, I/O, I/O, memory, memory. But the whole idea right here, we have two memories. Don't worry about those lines because these are still buses. So when you say data bus, we have a bus that takes the data and we have a bus that takes the address, because let's just look at it. If you have a memory right here, right, and you want to store something in the cell, you need to know what is the address. It's like a hotel. You're going to go to a hotel and you're going to say, hey, I want to live in the 4th floor. What room? Because everything has an address, right? If you want to go and visit a friend, the first thing you're going to ask them, what is the address? So it's the same thing. If the CPU needs to fetch something from the memory, it says, where did you store it? So if you want to store 5 in here, you have to tell me what is the address of this 5, right? So who's going to decide this address is the address bus. Okay, once we decide this is the thing that we want to move, so now we want to move 5. How are we going to move 5? We need a data bus. So the data comes to the CPU to process things and get it back to the memory. It's based on data bus and address bus. Okay, And here with the I/O, we also have a data bus and address bus as well. You only see the data bus right here. So the difference you guys gonna see right here is that the program, it's the memory. Here we said we have one memory, but this memory from within that memory, we're gonna divide that memory into a data and what? Code. And Harvard architecture, no. It says we have a program, a memory, a physical different memory for the program and physical memory for the data. Because every program has a what? Has the instruction and the data. So when I say A equal to 5, that is data. If I say integer, A equal to 5, right? And if I say scanf, I would say scanf is a program by itself, but if we assume that this is an instruction, right? So that is the program. You see what I'm talking about? So put the data inside a section in a different memory and put the program and the instruction in a different memory. That's the whole idea. And the Neumann, von Neumann, it says no. Memory is one physical memory, but divide the memory from within. So this is what you're going to learn in assembly. We have dot data, we have dot code, we have dot stack, we have dot heap. But are these, all of those part of your program is in one memory. So you have your program has data, your program has code, your program has stack, your program has heap. So just focus on these two right here, data and code. So these are going to be in two different sections inside one memory. Here, no. The data is going to be in the data memory, the code is going to be in a different physical memory. That is the whole idea. So because this is easy to implement and produce or manufacture, so that's why I think that's what I personally believe why it is very popular. Okay. So this is the von Neumann. This is one physical memory. This is data program, and so on and so forth. If you are confused about data program because you're coding in Java or Python, you don't see this. We're going to see what a data is and what a program is when you write a program in assembly. Okay. So if you look at the von Neumann, it's just one memory. If you look at the Harvard, it's two different memories. Do you see it? It has buses in here that handles the data, and then buses here that handles what? The program. So the difference is actually in the memory. All right. So and von Neumann says one memory. Harvard says two different memories, for one for program, one for data. But von Neumann says no, one physical memory. This is what you guys are accustomed to, which is what accustomed to see or to know in your computers, which is random access memory, just one random access memory. Here we have random access memory 1, random access memory 2. So that's a little bit expensive. So this is the commonly used architecture nowadays, okay? So hopefully now you know what's an architecture. So architecture is a CPU, a memory, I/O, and buses. Two types of architectures, which is von Neumann and Harvard, and we know the differences between both of them, okay? So just keep that in mind. So we're gonna focus here in the instruction set architecture, which is ISA, and we're gonna see what's instruction set architecture. So before we go that, we're gonna look at the differences between architectures. So what is, like if I have CPU, it's 86, right? x86, and I have maybe ARM, right? Architecture. So these are two different architectures, right? If I want to know the differences between them, I can focus on the length, the size, the speed, CPU architecture, number of type of registers. We would know what registers are because this is something new for you. You haven't used this in a high-level languages. And the instruction set. So everyone has its own instruction. All right. So if you have the address bus and you have the speed, the instruction execution, that's the hertz, and this is what you call the clock rate, okay? And the CPU architecture, is it going to be Harvard or is it going to be von Neumann? And if it's von Neumann, because mainly these are what the things are, how things are organized, how many registers you have. Do you have more or less? And the length here, we're talking about the data word. Can you store 4-bit, 8-bit, 16-bit? That means 2 bytes, 1 byte, 4 bytes, 8 bytes, and we're going to have 16 bytes. Okay, so these are the main idea of the differences. The addressable memory, the size of the addressable memory. Are you going to access a memory using 8-bit? That means 8 lines. Okay, so if that's 8 lines, then you're going to say 2 to the power 8, and that's going to give you 256. So that means you're going to access 256 cell. What if I give you 16? 2 to the power 16 is going to allow you to access more space. So that's going to be 32,000 cell. If I give you 32, you're going to access 1 billion cells. So that is going to differentiate a microprocessor from the other microprocessor. We're going to cover those in more details, but today we're going to focus on the instruction set. Okay, so what is the instruction set? Okay, so the instruction set is basically the interface between the hardware and the software. Because if you look at this code right here, this code is basically says move 5 to EAX. EAX is a register. Okay, so it's a register, it's a space inside the CPU. It's not a memory, it's not random access memory, it's a register. And we have 6, which is an immediate in here. We're going to say add 6 to 5. So this 5 now is going to be gone, and we're going to have 11, right? We are doing the same thing, but in ARM architecture right here. We're moving 5 to R0, 6 to R1. So R0 and R1, they are registers. So the name of the registers is different here. And the idea we add here, we're adding R1 to R0, and we're storing the result back in R0. So if you see the semantic and the syntax is completely different, right, guys? And even the language itself is different. You agree with me? Okay, so if that is the case, this is what we call the instruction set, because this instruction set's for ARM here. This is an assembly. This is not a machine code. This is going to be translated to the instruction set. Every instruction in ARM has an equivalent instruction set in here, okay, or have an equivalent instruction. And that's what we call the machine language. If you are confused what is instruction set is, just think of it as it's the machine language. So the same thing, move here is not the move right here, because here it moves immediate, and this is the way we move immediate. So when we move an immediate right here, did we have this sharp symbol? No, that is the syntax and the semantic. Why this is done in this way? Because Intel has its own instruction set. So every microprocessor, when they design it, they design the hardware, and in order to operate or to control the hardware, you need a software on top of it. That is the instruction set. So all programming languages, whether it's assembly, Java, Python, whatever, if they have assembler, interpreter, or compiler, those things they're gonna translate into the instruction set. Okay, so the instruction set is the one that's gonna help the software interact with the hardware, and the hardware interact with the software. Okay, so this is very important. So I want to keep in mind that if I say when I talk about the instruction set, especially right here, I always tell my students, just think about this part. So can you read this statement? As an English speaker, definitely no. You don't know it, because your architecture, okay, has an instruction set, and part of your instruction, you don't know how to react to those words. Okay, so that is exactly your machine language. That is your mind language, right? So you've been trained to understand that, right? So if I say, do you know assembly? Right? So you said, yeah, I can read this, because you get the input, you translate it, and you react to it, right? Because this is part of your ISA instruction set. So this is exactly when you are trying to execute ARM in here. The Intel gonna say, I don't know this. It's like when you, as a speaker, you're trying to translate this. You're gonna tell me, no, I can't. But when I put it in the right instruction set, you know it, because your brain is like a hardware. It's already there. When you were born, brain has an exposure to a language medium, right? So either your mom, your dad, or both of them, and that is how you build your instruction set. Okay, and that's what you start like taking instructions, interacting with them, and doing things based on that. Correct, guys? So it's exactly the same applies to here, applies to the computers. So there's the hardware, that's the whole brain, and this brain is going to interact or do things based on instruction sets. So these instruction sets are within the CPU. They are built inside the CPU. Your program is outside of the CPU. But if your program needs to be executed, it must be within the instruction set domain. Okay? So that is that. So when we look at the implementation right now, we have different implementation. These are all von Neumann. Okay, so this is very important and very confusing questions when I ask my students, what is the different computer implementation? So we either implement von Neumann as a stack or as accumulator. We're going to cover those later, or register memory or register. Okay. So if you look at the picture, just looking at these two pictures from this here, okay, you're going to see like in the registers, the memory is not linked directly actually with the CPU, with the ALU, arithmetic logic unit, and the registers. These are the registers, okay, memory inside the CPU. We're going to talk about this in more details. So look at the ARM right here. You're going to say move C to R0. That is the register. Just imagine this is R0. Move D to R1. So this is also R1, and this is going to be C, and this is going to be D. So you as a programmer have to move them because there is no direct link in here. You have to move them. Once you move them, then you need to call what? The ALU, which is the add right here. You say ALU, and this part, arithmetic, means addition, subtraction, multiplication, and division. You're just going to take one of those, and you're going to say, hey, you know what? I already uploaded R0 with a value and R1 with a value. Please go there, do the addition, and give me the result back. So this is going to be maybe the result is going to go back here to R0. Okay, whereas if you look at the Intel right here, you move the memory C to EAX. So you have a memory, let's say here, okay, C, okay, and you moved it to a register somewhere, maybe this one. So this is maybe EAX. And you said add to EAXD. Did you need to move this? No, because you must have one register loaded, and the second argument or the second operand, it doesn't have to be a register. It could be a memory, it could be a register, it could be an immediate, it doesn't matter. Okay, so that's why we call it register memory. It doesn't have to be always register memory. It could be register immediate, register, but at least if you're dealing with the memory, you cannot have both memories. You cannot say add memory 1 to memory 2. That's not possible in register memory. Okay, you have to have at least one. Here, not even possible to have one memory. Both of them have to be registers. Okay, so this is what we call x86, and this is what we call ARM. Okay, so in the register memory, you need to have one of the operands as a register, and one of the operands, and the second operand to be either register, memory, or immediate. But in the ARM, which is a register, you have to load and store the values here first, and then you're going to call the ALU. So when I say there is no link, I'm talking about programming wise, okay? So you have to do it yourself. You're not going to expect the CPU to go and fetch it. Like here, if you say D, and x86 is going to go and fetch the D from the memory without your help. But right here, no, you have to do it yourself as a programmer. You have to move it to the CPU because the CPU is being designed, or the architecture is being designed to work in that way. All right? So let's look at the programming. So now we know the level 0, the level 1, and this is the instruction set. Do you see it in here? So you have the hardware in here, which is we call the gates, the circuits. This is what you guys learn in your introduction to computing and everything. And this is the microcode or the hardwired gates and circuits. And then we have the instruction set on top of it. So if you have the instruction sets on top of it, you need to communicate with it, right? So you need an operating system. Why you need an operating system? Because you need to write a program, right? So this program could be an assembly, it could be a C, it could be like just a program, right? That's like out of the shelf program or something that you write yourself. So this is a high level language. This is what you see in here. This is like the assembly language. This is the system software, which is the operating system or the library code. So we're gonna just look at the paradigm of programming. So if you look at the register right here, you have the register right here. If you look at it, so this is a register architecture. This is the ARM architecture because Raspberry Pi uses this architecture. So if you look at this part right here, this is mainly what the main components are. So this is what we call registers. So you have what? You have A, B, C, D, and E. These are registers. Okay. This is the ALU. That's when you have the instructions in there. And these are the buses, right? The address bus, the data bus, and the control bus. So the control bus is going to say read or write. So first you have to tell me where are the things that you need to read or to write. Once you decide them, you said, are you want to write to a memory or read from the memory? That's when the control bus is going to come to the place. Okay? Once you decide to read or write, you want to take them from memory to registers here, A, B, C, or D, or you take them from the registers out to the memory. So you need to say read or write, and then you need to put them in the data bus. So the data bus links the registers with the memory. Okay? And if you notice, we have two ALU. You might wonder why. Okay? But remember, we have a floating point and we have integers. So we have a different ALU for floating point, which is real numbers. And we have also ALU for integers. All right, so what's PC? That's the program counter or the instruction pointer. We're going to cover it in more details. This is the instruction register. Okay, so if you have, remember when we talked about the Van Neumann in the Harvard, we said program and data. So if you want to fetch a program, which means an instruction, then you need to decode this instruction. Okay, so you need to decode what type of instruction it is. So once you decode it, you would understand, is it add, is it subtract, is it multiply, is it divide, what it is exactly. Once you know it, then you're gonna tell the ALU what to execute. Is it gonna execute the add program or the sub program or the mul program or the deb program and so on and so forth. And we have something also in here we call the flag. We're gonna talk about this in more details. Remember, this is just the big picture. So these are the terminology and the terms that we're gonna use during this course, okay? So this is the memory. So this is what we're gonna do. So the address bus, are we gonna read this memory? And if we decide this is the thing that we wanna read or write, that's gonna be decided by the control bus. And once we do, we're gonna upload it through the data bus. Either it's gonna go to one of those registers, do the processing, and then produce the result back to the memory, or vice versa. Okay, so if you look at this program right here, we've been talking about program and code and data. So if we say load 10 to A, load 15 to B, and add B to A, you see it in here, and store the result A where? In 20. You see it? So this is load, load, add, store. So this is what we call the code, okay, or the program. And in this, it's one memory. That's like the Van Neumann architecture. It's just one memory, but this memory is divided. So remember, there is no two different physical memory, just one memory. I'm just showing you that these are two different sections. So this is the program memory. The data memory here, it is going to be the A and B. This is the data. Okay, this is where you're going to store it. So you want to store the result back in where? A, you're going to store it where? In 20. So I'm sorry, A and B are the registers. 10, 15, and so on are actually the immediates, right? 20 is the memory. That's when you're going to store it. So that is exactly what the memory is. Okay? So this is when you put it all together. So this is going to be the program, okay? And then when you add A to B or B to A, you're going to get the result. So store the result in the data section, which is the memory, was going to be 25. If you add 10 to 15 is going to be 25, and you're going to store it at the location 20. That's the address. Okay, so that's the address bus. 20 is the address bus. 15 is the data that you need to store. Okay, and store right here, it means what? Write or copy from the registers to the memory. So that is going to be handled by the control bus. Okay, so these terminologies are very important. Programming, program counter, we call it instruction pointer in x86. In Linux systems, they call it PC. We call it IP in here. This is the instruction set. We're going to talk about that in a minute, and we're going to have a flag. A flag is a very core components of what we're going to do in this class. If you want to do the same thing in register memory, it's going to be straightforward, right? So this is going to be your data section. So you have 3 variables, and you're moving A to EAX, and you multiply B with A, okay? And you're going to get the result back in A when you multiply them. And then you're going to add C to EAX, which is the multiplication of A with B. And then you're going to write the result back to the monitor, okay? So this is exactly what you need. You need an assembly language, an operating system, and instruction set architecture. All right, so in x86, this is going to be your program. You have the data and you have the code. Okay, so we have something else we call the instruction cycle. We're going to talk about this in more details. Again, this is just like the big picture of this class. So if you look at the instruction cycle, if this is the code, so this is add EAXC to EAX, this is going to be the code. If you want to execute this, the CPU needs to do something about it, right? So this is what we call the instruction cycle. We have to fetch, decode, fetch the operand, and execute, okay? And store if the results is required. So this is the whole cycle. We're going to talk about this in more details. But we're going to cover in this class something we call instruction cycle. We're going to focus on that in more details. So in order for this to happen, this is going to be the cycle. We're going to cover this in more detail. So just showing you the terms and the components that we're going to deal with. So you're going to be right now, you're going to say, oh my God, what he's talking about, I'm confused. Don't worry. This is just the big picture. I'm going to focus on this in more details. So first we have to fetch the whole instruction right here. And then we have to decode it in order to understand that the CPU understand that's an add. And once it does that, does it have a memory operand? Yes, it has a C, go and fetch it. If it doesn't have a memory operand, it's just gonna ignore it. And then once we have everything inside the CPU right here, then we're gonna do what? We're gonna execute it. Once we execute this part, if the destination right here is a memory, we're gonna store, but the destination is not a memory, so we don't need the store. So the main idea right here, you only need fetch, decode, and execute most of the time. You need store if your destination is a memory. Again, just to show you what's the instruction cycle and what are the main terms of the instruction cycles, we're gonna cover them in x86 in more details. And remember, this is sequential. We do this instruction and then we go to the next, and so on and so forth, right? All right, but we can do this instruction cycle in parallel, and that is exactly what parallel programming is all about. So instead of taking one instruction at a time, you can take multiple instructions at once. Why? Because in your microprocessor, you have 4 cores, and every core is a processor by itself. So instead of doing add to EAXC at one time, you can go to the next instruction, maybe subtract from EAXD, and then you give it to microprocessor 2, and so on and so forth. So that's going to save time. I'm not going to focus on the instruction cycle for parallel. We're going to focus on the instruction cycles for x86. Okay, so with that, hopefully you are around here. If you are here, you're fine. If you are around here, do not be intimidated. Just that shows that you need to put more effort. Okay, so it's all about what you know, and what you lack, and what you need to improve. So this is mainly the big picture. And this is, as I said, is not part of the book. This is something I always like to share with my students to show them where we are heading, okay? So this is it for today. And I'm gonna upload these to the iCollege. And we're gonna meet I'm gonna meet with you guys during the office hours, okay? Thank you for now, and see you later. Thank you, guys.